So where and when were you born?
I was born in Virginia in 1946.
And what month? I'm interested in people's astrological sign.
Okay, December 29th. But I'm curious about what your slant is on the interview because it seems very sociological and
That's my background. And so what I'm
yeah,
interested in is two things. I'm interested in the scientific findings, and then my other interest is what is it about the background of these visionary scientists, or one book called it Rebel Scientists, that allows them to take on the establishment. I mean, people like you went to Ivy League colleges and worked in traditional science. Why can you defy it? So it takes, it's a profile in courage as far as I see it.
I
So,
don't see it that way at all. I
oh,
mean, I mean, I mean, to me, science is about the truth, but trying to understand the universe. And the real problem right now is that our science is that there's a big bureaucracy involved. The government has to fund most of the research that gets done, and so it's the system is sort of rigid and a lot of inertia involved. So you kind of have to be independent, I guess, to be able to look at questions deeper. I mean, I go back to an experience I had in grad school when I told my advisor at some point, well, unified field theory is all I'm interested in. I want to have the deepest theory of the universe. That's all I care about. And he said, well, the problem is we'd like to get our students out quick. We'd like to get them out quickly. And 3 or 4 years and out.
yeah.
And Einstein worked 40 years trying to do unified field theory and did not succeed. So that we'd like to have you do that later. And they said, basically pick easy topics that you can get papers done. So when time comes for tenure, you have a stack of papers that you published, and then you get your assistant tenure, your professorship. And after 10 years of doing that, solving things you're not really interested in, then if you get tenure, now you can work on things that
Yeah.
matter to you. And I thought that does not sound very interesting to me. So I decided to take the more private route, work in industry, and I figured on the side I would do the great problems because I wasn't going to have time as a as a professor, doing these things. So it's really just curiosity, just trying to look at them, and also I think that kind of pressure to publish or perish. I realize I'm looking down at your face, but the camera's up here, so I don't know, it's probably a little weird, but so that pressure to publish or perish and to get grants is a problem for academic science. You can't really look at the deep problems in the system. So it's not really rebellion; it's just wanting to have a deeper understanding.
But that turns out to be a rebellion against the system. It,
See
whatever
that
the motive.
I don't feel that way at all.
Okay. So what month were you born?
December,
Oh, that's
December,
right. So you're a Capricorn.
right? Yeah.
And do you identify at all with being a Capricorn, or do you think astrology is hogwash?
I think it works. I think the Capricorn is good as far as tenacity and you know stubbornness or persistence, if you like. So I
Yeah.
think that part is helpful.
Do you know your Myers Briggs personality type or Enneagram or any of those interesting personality types?
Um, the Enneagram I do not know. Myers Briggs is probably INTP, something somewhere in there probably. But some of those boundaries feel kind of artificial. They kind of really kind of you're kind of in the middle, kind of X, not really, but you have to have some P to look into the deeper problems, and you have to have some J to ever complete anything. So
Yeah. My thesis was that people would be intuitive rather than sensing who are interested in this kind of visionary work. And so far, I've only had one S, and everybody else is an N.
yeah, yeah, and as far I said NTP, but really it's probably more F. The F helps the intuition, while the T tends to be the people who are more rigid. So um, it's hard to say.
I was surprised that so many people that I've interviewed are P's because I thought if you go through graduate school or med school, you've got to be a little OCD compulsive to jump through all the hoops. But somehow people manage to be P and make it through the hoops.
Yeah, I think the people who are higher up in the existing system probably are more T, and the ones who are more in the alternative areas have more F involved because the NFs are the intuitors usually. The more That's what I find at least that
Mm-hmm.
the people in the intuition areas NF is kind of a classic.
Yeah,
So
right. What was there about your childhood that led you to study physics at top universities? What was your family background like?
I had a mother who answered my questions and was smart and tried to talk to me when I was little, you know. So I felt there was encouragement there. That was the biggest thing.
Um, and then I'm sure you were an excellent student,
Right. Yeah.
so that helps. And then why did you decide to study physics and not anthropology or something else?
I in a way I just sort of fell into it. I think my curiosity was trying to understand the deep questions of the universe. I wanted to know how things worked at the deepest possible level, and eventually it seemed like physics was the best way that you could answer a lot of those questions. Um, but it wasn't really obvious to me early on what I was going to do. I think Richard Feynman's books, the Feynman Lectures in Physics, which had just come out about a year before I was a freshman, I discovered those, and that's really what it was so much fun and so inspirational to read him. That's what made me say, okay, hey, this sounds like fun. I want to do this.
I'm wondering if it's kind of a shock to be like the smartest kid in high school and then go to MIT and Princeton and everybody else is just as smart as you are.
But yeah, that's always the challenge. And I knew it was going to be. Um, and I, it was a small town. It was a small country town, basically in rural Virginia. So um, it's quite a change. I know when I got to Cambridge, I said hi to everybody on the street because I grew up in a small town and I was used to doing that, and I restrained myself and sort of start learning how to act like the big city kids act, which is sure that's a shift. Um, so yeah, and I knew that the whole thing with a lot of kids would be very smart there. I knew that. So um, I still had to deal with it a little bit, but it's also nice to have smart people to talk to, so you can share ideas and things. So um, I was prepared for it, I guess, in a way.
I'm wondering, I'm sure when you were an undergraduate and graduate, it was mostly men studying physics. And I'm wondering if people said, where are the women in our classes?
Well, this was in the 1960s, so people didn't think much about that. Mostly they were just glad to be there. um, I know that MIT had a woman's dorm, and but there were very few women interested in physics. There would be more mathematicians, more in other areas like biology and things like that, but not so much in physics. Um, when I got to grad school, it was 1969. Princeton was really trying hard to recruit more women, and there were out of a class of maybe 22 people who, in that year in physics, there were maybe 3 women. Um, and they had to kind of bend the rules to get more women there because it was very selective. And I think 2 of them dropped out eventually. So that it was the mathematicians who were women did much better,
Hmm.
and in other fields. So it was something about the female or the energetics or something that seemed with physics it was more difficult and more for some reason. And I think mathematics is more linguistic, and women tend to be very good linguistically. But in the physics sort of combines a couple different areas of talent, so it was more rare.
What was your family growing up, their attitude towards religion and spirituality?
My mother was very uh, devout. We went to Methodist church, and that was not an option. So we went regularly. I mean, I began to discover, because I was thinking about it scientifically. You know, how is it possible that I just happened to be born into a family with the right religion? Uh, you know, uh, because the Baptists across the street had different beliefs. They didn't believe in dancing. We did, and other religions had other different beliefs. And so how was that possible? That didn't seem to be very likely. And so you begin to wonder how this can work out. And so there's something wrong clearly with this picture. And about age 13 or 14, I began questioning. I began realizing if it's written in a book, it doesn't have to be true because human beings write books. So I began thinking for myself and said, well, okay, what's the evidence that God is real, right? It's what's the evidence that all these stories in the Bible are true? Well, that would be the miracles. The miracles are the best proof, if you want to say, that these things are true. But I wasn't seeing any miracles around me growing up, so you kind of begin questioning. And about age 13, I came across Mark Twain's book, A Connecticut Yankee in King Arthur's Court, in which the Yankee gets hit on the head, goes back in time in Arthurian England, and makes up this story about there's dragons, and he had all these heroic things he had to do, and I guess the knight who captured him did. And I realized, oh well, he's just trying to build himself up, and so that could be how some of these stories get created. That like fairy stories and all that, maybe somebody just made them up to embellish their own point of view. So all of a sudden I began realizing it doesn't have to be true just because it's in a book. So that was kind of a revelation for me, because until that point I unquestioned hadn't been really questioning books. So that was kind of like my beginning to become more broad-minded, and I realized, well, there's no real solid evidence for any of this. You have no proof of any of it, and so you have to back up. And so I think that it was kind of a scientific approach, really, to religion that kind of got me to shifted my worldview, and that pretty much held true for the next 30 years. Because I didn't see any evidence, it looked like science had all the answers, and So the scientific view, and we knew that our rocket ships worked, and our cars worked, and our radios worked. So our science seemed to work okay. So that's encouragement. And the way you're educated in school, um, you're taught the theory in the textbooks, and then you go into the lab and you do experiments, and they verify the textbooks. So you get verification. So I say, oh well, they must be right then because I just proved it. Um, in those days, it never occurred to me that maybe there were some experiments that they didn't show you. You know, maybe there were some other parts of this whole system that they weren't talking about. It never occurred to me. It looked like it was a coherent system, and I think many scientists who sign on with the conventional point of view today are still in that state. Um, in the 1980s, I began hearing rumors about remote viewing. Okay, remote viewing, I began getting the information was actually very accurate and successful, unlike what they would have you believe in the public. And the more I looked into it, the more I realized, well, this stuff is real, and yet our physics can't explain it. In a sense, that is a miracle, okay? It certainly is a place of where our physics falls short. And once I began looking into that, I found dozens of other areas where our physics also falls short. It doesn't really talk about or think about or publish. So you can't really publish papers in the physics journals on these subjects. They won't let you. They won't publish them, even though they're very important to reveal the shortcomings of our present science. So that's kind of what got me on my present track. And I discovered there's so much out there. There's so much information that I just never would have looked for before. And you take a book like Psychic Discoveries Behind the Iron Curtain by Ostrander and Schroeder. It's a classic book from 1970. These two women who went to Eastern Europe and Russia in that time period and discovered that the governments there were involved in large research programs looking into psychic abilities, healing abilities, all these extraordinary areas that really defy conventional science. And the governments were interested in them, and they had military applications. And the deeper I looked in, I began to realize our government does this too, probably, maybe not as much, but it's all kept secret. So that most physicists don't have a clue about what goes on. So, there's this big split in our science between those who look into those questions and those who don't. And so anyway, that's just been fascinating to me.
Were you at Princeton when they were working with the random number generators, Nelson and Jane and Brenda Dunn?
No, they were just beginning to, and I didn't know anything about it. By coincidence, I happened to meet Robert John. I was doing a postdoc in the Aeromechanical Sciences Department, which is engineering, which he's the head of, and I was taken over to his lab and met him, and he was, as far as I knew, and as far as he was admitting, working on ion propulsion for rocket flight, okay? And he was doing some of that, but I think he was just starting the Paralab when I was over there. So I knew nothing about it until later.
After doing all this work, what have you concluded to your boyhood questions? Is there God? Are there miracles? Is there an afterlife?
Yes, yes, yes. Yes, yes, and yes.
And then how do you define God at this point?
That's what my third book is all about.
Oh, yeah.
I just finished the third book, Science of the Soul, the Afterlife, and the Shift. And it's kind of the culmination of that little avenue of research. But it's a continuation of the earlier work I did on ESP and all the paranormal things in the first book. And in the second book, I discovered the life force energy, which is what the Chinese have only known about for 5,000 years. They call it qi. It's what the Russians call torsion. So, by following my nose, I eventually got to these really deep questions. And it takes you to God too, but what you find is that the human psychic ability is connected to these other energies that our present science doesn't really talk much about. Um, the energies that make remote viewing possible, they make out of body experiences possible, they make levitation, teleportation possible. These other rules that our present science is mute about. And torsion is a big part of that. And the soul is part of that. We have energies in our body that so shape our personality that are not material in the conventional sense. And so when the body dies and it's cremated and is buried or whatever, these energies still exist. And that's what makes the afterlife possible. And that's what makes our intelligence and our consciousness possible. So mediums can still talk to somebody just as well after they're dead as before because it's telepathic anyway. So it's these other energies that are involved in that.
And
So,
is the other energies equate to consciousness? Does it equate to the quantum information field? How do you describe the other energies?
well, it is consciousness, the energy that what I would call it torsion, and I would also call it consciousness. They're all part of the same thing. Um, and I don't. I think that we've been kind of sold a bill of goods by our public media, by our scientific establishment, who want us to think that the existing science will just explain everything. And they're always, I mean, you see this in relativity, general relativity, or gravity theory, a lot, which bothers me. I was in the gravity group at Princeton when I was doing my graduate work, okay? The gravity group is interested in experimental cosmology. They have developed instruments to look out into space and, try to measure these deep questions and things like that experimentally. Um, but even then, it seems like the establishment has been pushing Einstein's general relativity theory ever since it was created in 1916. Okay, so 100 years later, the standard theory is still that particular theory. Okay, they try to explain everything based on it. Even Einstein knew that it wasn't right. Okay, he continued to work for 20 or 30 more years. He developed 8 or 10 more papers that were extended beyond that theory, including new phenomena and new equations, which are not taught in general in school in the U.S. It was never mentioned when I was in grad school in the gravity group. And we had some of the top physicists in gravity in our group, and yet it wasn't a question. One of the principal papers wasn't even published in English in about 1996. It was translated in 1996 by 2 private individuals. So we've been kind of ignorant of these new alternative views that are really kind of part of science, but they haven't been publicized in the larger community. So what that leads to is when you find problems with astronomy, you find things aren't behaving the way they're supposed to, instead of saying, well, that shows Einstein was wrong, we got to go back and fix the theory. But they don't do that. They say, there's something missing. We're going to call it dark matter, which is a fudge factor. They can't measure it. It's just put in there to make to cover up for the discrepancy. And so this is an issue with the way the science has been working. And so it's frustrating when you're watching this. So I'm interested in trying to do something better than that. And it's all connected. This is all connected with the torsion and with the other phenomena we talked about, the consciousness, etc.
Well, I know this is kind of difficult, but can you summarize for readers Einstein's general relativity theory and then a little bit about how it was tweaked with later papers? E equals mc squared?
Well, that wasn't a later paper. That was an earlier paper, actually. But what Einstein had created his special theory of relativity in 1905. Okay, that was the first thing he was trying to address, is what happens when things move fast. Okay, when two frames pass each other at very high speeds, because they knew that light was finite, and they were trying to, and we had two different basic theories in those days: Newton's theory for gravity and all of matter, and then they had Maxwell's theory for electromagnetism. Okay, electricity and magnetism. And the two theories didn't predict the same thing about what happens at high speed. They had a conflict, and he wanted to resolve that. So his special theory was he had to tweak basically Newton's theory to make it consistent with Maxwell. And to do that, that's where his theory came from. That's where E equals mc squared comes from, and the idea that light is the limit of the speed. Okay, that was 1905. But then he realized, okay, we got a problem here, because this theory works in frames of motion that have constant speed. Are we okay on time? Are you watching something? I'm not sure what you're watching.
I was just looking at my notes.
Okay. So that works okay when things have constant speed. What happens when they accelerate, when one is accelerating versus the other? Then how do you do it? And he also realized that gravity does that. Gravity accelerates our frames. When you fall, you speed up. Okay, so he had to go back now and figure how to add gravity and how to add acceleration to this original theory, and that's where he ended up with general relativity. It took him about 10 or 11 years to do that. So 1916 he was trying to put them all together. But there are some simplifying assumptions he made. Okay, basically, he came up. It led to the idea that space-time can be curved instead of, it's not just flat and the same everywhere. It can be curved, and you could treat acceleration as a curving of space-time, and that means gravity could be treated as a curving of space-time. Okay, so you get this idea of a mass and then bending the space around it. And so when something goes by, it's trying to go in a straight line, but it goes in a curve because it's just trying to do what looks like a straight line to it, but it happens to be in a curved space. So that was his original theory. And that's what led to Eddington's experiments, bending starlight, that was a great confirmation of Einstein, 1919. But it troubled Einstein because he knew he was making some simplifying assumptions. He was leaving out the possibility that space can have a twist to it. Okay, he was treating all matter as though it was little point particles, like little billiard balls of point particles, and it would work okay if that's what matter was. But he knew that it wasn't, and they were learning during that time period that actually most matter has a spin, like a proton, electron, neutron. They all have spins of a spin and a half. They all like little tops that are spinning. And that means they have a special direction. And if they have a special direction, then his theory was not complete, because it couldn't describe what happened for spinning particles.
Because they don't necessarily want to move in a straight line?
Yeah, because the fact that they carry a spin when they're in gravity or being accelerated will affect how they move. So that spin will contribute to their motion, and it was not in his equations.
Wow.
Okay, so he had to go back, and by the next 10, 15, 20, 25 years, he had several later papers, 1928, 1930 or something, where he published a couple more, where he tried to put in, to expand his idea to handle spin. Okay, and that led to the idea of what we call torsion. Okay, I'm not sure that his version of torsion is the right one, because it seems like the Russians and probably even the Germans before that had gone beyond this. But a lot of this stuff is kind of murky, so we're kind of trying to reconstruct history after the fact. But the bottom line is that for spinning particles, you need to have the torsion, and you need to have this expanded theory. And the standard theory that is taught in school is his original theory, which can't really handle that. And it's like physicists just go around with blinders on. They don't want to look at these questions. They just so anyway. That's how things work in the real world.
So if we look at planets, they orbit because of gravity, right? And
right.
they spin. So does torsion apply to big matter like planets because they're spinning?
It does, and some of the torsion, some of the spinning of the objects is handled okay in gravity. Okay, some of it is handled okay, but for the point particles with their own internal spin, it does not look like the old theory handles that correctly. There's an extra part. There are the best. I mean, you have to kind of make your own choice as far as what you believe. Um, then this is a problem in physics because it comes down to intuition. A lot of physics is intuition because there are so many theorists out there cranking out papers. You know, you would not believe how fast and how many equations are out there, and they all claim they're the right ones. You know, and so how do you decide what to study and what to analyze? My own path has been that when I was working on the second book on life force, and I had already concluded from lots of experimental evidence that there was a special force. The Chinese have been doing this for 5,000 years. It's a part of their traditional medicine. And these experiments are well known. They're codified in their medical science. But then in the West, in the last 200 years, other scientists have rediscovered this same strange energy. Baron von Reichenbach in Germany in the 1850s did 40 years of experiments on this energy. He found that some people, when they have health challenges, or he called them high sensitives, they can sense this special energy and they can actually see it. It has a color to it. They can describe it, and he would do blind tests in darkened rooms, give it about a half hour to a couple hours in light and dark conditions, and your eyes begin to see this stuff. So he would cross test different people to make sure they were describing the same thing. He would try to trick them to make sure there was no deception going on. And so as a result of things like that, a whole empirical science of this extra energy has developed.
What did he call it?
He called it orgo. He called it ode, O-D.
And orgo and energy is from Wilhelm Reich, right?
Yes, and that is the same stuff. Reich came in as a medical doctor in Germany, different education, later, and began doing experiments, but he discovered it as well, okay? And so it keeps getting discovered, and they gave it different names, but it's all the same energy. And the Russians discovered it in the 1950s, and they call it torsion. And they had a much more scientific attitude. They have a whole government program devoted to it.
But torsion means the twisting, right? The vortex that's created.
Exactly. In other words, the life energy, the chi of the Chinese is the same thing, but physically it appears to be connected with the twisting of space-time.
And how does this apply to string theory that says everything is this vibrating?
It doesn't. It doesn't. String theory, from what I've seen in 30 or 40 years with some of the best mathematicians in the world, has not really had any great successes. It has siphoned off a lot of very top mathematicians because the government was funding this area, and it may still bear fruit at some point. But there are a lot of thoughtful physicists today who think it's a dead end or a blind alley. They didn't really understand what they were doing. And the reason, I think the problem is, here's the problem, that it started out back in the 1960s. Physicists were banging particles together at high energy and seeing new particles getting created. And they were trying to make some mathematics to describe what they were seeing. And some of the new particles obeyed an equation that looks like the equation for a string. Okay.
Is that like a Higgs boson?
Well, that you eventually get down to that point, but not yet. No, not this. This is like the excited states of neutrons, of nucleons, of the excited states of that would be back where that came from. Um, so most physicists are very mathematical. Okay, most theoretical physicists are highly mathematical. In fact, the system tends to preferentially select for the most mathematical. They are the quickest at producing models. Okay, um, but that does not mean that their physical intuition is very good necessarily. But their mathematical intuition is great. So they see an equation for a string. They say, "Aha, must be a string," and they try to take this fundamental experimental nub of truth about strings, which must be part of the theory, and they built it into a very elaborate theory. Um, and one problem with it is that it integrates all of the other parts of physics that might be wrong. For example, it takes Einstein's original 1916 theory of gravity and integrates that into string theory. Okay, so that's folded in. So any problems with string theory could be because they took the wrong gravity theory. So you have all these, and no one's really checking. It's all done in a big hurry with lots of money being thrown at the problem. So there are a lot of people who have expressed some real skepticism about string theory, and I think the reason is because of the way it's been put together. There may be some aspect of it that's true, but I'm not sure they really understand yet, which part is true. So,
Gravity is a force, but it's not a material thing, correct?
yeah, there are lots. Gravity is a force. It's not a material thing. That's true. Um, Gravity is our present physics has been pretty successful. The theoretical physicists have been pretty successful at um, electromagnetic things, forces involving electromagnetism. Okay, Feynman's great work with the charge on the electron, be able to calculate how things interact at very small distances, was very successful. Um, but when it comes to gravity, they have a problem. I mean, gravity is well, the first problem is that electromagnetism is what they. I don't want to get too complicated here, and I'm sorry. Let me just back up. Gravity is the one force they haven't yet really successfully unified with the others. Okay, it hasn't fit together in a natural way. There are also reasons to suspect that our quantum mechanics is a very kind of linear theory. I mean, basically, you can add wave functions on top of each other. It's called the superposition principle in a very nice way, which makes the math very clean. But that's also kind of what is true for electromagnetism. Okay, that it handles linear effects. In other words, when you said two charges are twice as strong as one charge, okay, that's a linear effect, and that's true for electromagnetism. But gravity doesn't do that. Gravity is nonlinear. You add two masses together, and they create extra energy, and that is also like a mass and affects the gravity of the whole system. So it's not proportional to the number of masses. It's more complicated than that, and that will mess up quantum mechanics because quantum mechanics doesn't really kind of go along with that. So I'm kind of giving you a really rough. I'm trying to explain it in a very rough kind of way.
Sure.
But so gravity is still kind of an anomaly. I mean, physicists think it should have a quantum theory, for example, but it's so weak that it's very difficult to detect a graviton if it exists. Okay, the detections have not been too successful, so it's more theoretical than empirical. And there are lots of questions about gravity and about how it actually works, because just the fact that Einstein's gravitational theory is still being questioned. That we have now dark matter and dark energy that astronomers say needs to be included, but nobody has any idea how to fit that into his theory. Okay, so they're kind of just treating it like extra particles that they can't find. But it's probably what the Russian. What I find frustrating is that the Russians' torsion theory already explains all of this. The Russian torsion theory very naturally would say that the dark matter is actually left-handed torsion, and the dark energy is actually right-handed torsion, and that it's already in the Russian gravity theory. What happened is that when the Russians were doing their own programs in the 50s, 60s, and 70s, they were much more empirical. They would do experiments, and they weren't wedded to treating Einstein's original theory like a god or something. They were open-minded, okay, and they have a lot of experimental results. So I went back and looked at the best theorist among the Russians who was trying to work with those experimentalists in the Russian program. His name is Gennady Shipov, and he has his own theory, which he developed based on actual experiments and actual empirical data. And so I have more confidence in that approach. So I think something like that is probably the real answer. But there's a big communications gap between East and West. So for some reason, Western scientists have been very slow to take a look at it.
What makes the photon spin and have torsion?
Well, I'm not really sure that it, because it's massless. I'm not sure if it has torsion or not. I don't know, because the massive particles, the particles that have mass, like electrons, protons, would tend to respond to a torsion force. I guess photons may. I don't really know. I haven't looked at it. One of the problems has been that even though the Russians have published some of their results, they haven't published all of them. There have been issues. I mean, because this was also a classified military program in Russia. Okay, and when Glasnost and Perestroika happened in '93, they published a lot, and a lot came out, and we wouldn't have what we have now except for that period. But we did not greet their efforts with open arms, and I think that they've restricted themselves since then. So we have part of the story. We don't have the whole story.
So it is. So dark energy and dark matter act upon like an electron to have it spin and torsion. I mean, it's what's the origin of this movement?
What's the origin of spin?
Yeah. What makes it spin?
Well, that's a good question. And physicists don't actually think about that. They never ask that question. Okay. They never ask it. And this is, it's one of the frustrations with our Western science. I think that what physicists learned back in the 20s and 30s when they developed quantum mechanics and they had their little particle experiments and things, they developed a theory that could explain their results, that could predict successfully the outcome of some atomic experiment, for example, or some particle collision experiment. But they also realized that their theory was very counterintuitive, and basically they adopted the philosophy of don't ask. Don't ask, don't tell.
Just calculate. Shut up and calculate.
Keep your mouth shut, right? And I heard I heard it as an anecdote by some Nobel Prize winning physicist who I knew, who said something like, um, "Oh yeah, Joe Blow, he went crazy because he was trying to understand quantum mechanics, you know." Um, and Richard Feynman in his books, he says, just take the equations and calculate the results. That's all that really matters. And he's very intuitive and he has good pictures. Uh, and he's one, but still, it's the prediction, the mathematical prediction. That's all you can really have. So they kind of adopted that attitude that you can never understand it, don't try. And I don't accept that. I don't like that idea. I think that we need to have an intuitive understanding of things. Um, and it probably means we don't understand it well enough if we can't give a coherent explanation for it. For example, with spin, um, some physicists have tried to explain spin because really what happens is that there's energy in space. Okay, there's lots and lots of energy in space all the time. It may look empty, but really there's photons and other kinds of energy flying around. It's called the 0 point energy. Okay, and if you look at a particle, it's not really sitting still. It's really jiggling around a lot. Okay, even the Germans knew this back in the 1930s. They called it Zitterbewegung. It's like random walk, and that same random walk also leads to spin. That causes them to have a little orbiting motion as well. Okay, as a back and forth motion. So there are some scientists who take the attitude that should be part of the picture, and I agree with that. But it tends to make it more complicated. Then you have to. It's a deeper level, and I've been kind of surprised that more scientists don't take that attitude. That they seem very happy with taking a method they can calculate with, make their predictions, get their papers published, and move on. So it'd be nice to have more deep thinkers and deep questioners.
Why were they so excited about discovering the Higgs boson in CERN?
It's a good question. I look at some of this stuff with the same attitude as a sociologist would, okay? Or maybe a psychotherapist. Because it's a sociological condition. The physicists make up a community that talk among themselves. They are dependent upon governments for their funding. So it's very important that they put out a story that is compelling to their funders. Okay? Have to produce a story that things are going great. We just got one more little thing to discover, and then we're going to have the whole thing figured out. Just another billion, another super collider, And so they have to put out that attitude. It's good marketing. And so the ones who are successful are the ones who take that attitude. I got very discouraged when I was in grad school because I was wanting to be a theorist, but every theoretical paper I would read, the author would say he'd solved everything. His paper was the last period, they all acted like they'd done a lot more than they really had. And he had put a lot of time into each paper before you figured out how flawed and how limited it was. But the whole community is like that. I mean, I get my Google News on my smartphone, and they're always announcing some huge physics discoveries all the time, and most of them are really overblown. The Higgs boson was needed because they had adopted a particular theory for particle physics that worked great, except that it predicted no masses. It left out the mass calculation, okay? It could not predict mass. So to save that theory, you had to have something that creates the mass, okay? And so the Higgs boson was what they came up with as the answer that would be responsible for the mass. And there are a lot of constraints mathematically on how you can do that, but that's what they came up with. But it was, to me, it looked like a sort of an artificial solution, uh, because it still leaves out gravity. There's still no gravity in particle physics, and you would think that mass would have some connection with gravity, but there was no mention of that in the Higgs theory. Um, but they really kind of needed it to save the rest of the theoretical structure, the so-called standard model that exists right now for the various particles. They needed to have it. Um, so they were really happy when they found it. Except I think that it's probably more complicated than they would like to admit. There's probably more than one Higgs particle, and probably if they keep looking, they're going to find that the theory, is only partly right. There's a lot more to it than this. So, it's I there is a, what's the name of the book? There's the Higgs Fake. There's a book called The Higgs Fake by a German physicist who is very disgruntled with the way conventional physics works, and basically, and he's a theoretical physicist. He's well trained, and but he talks about all the reasons why the whole thing's been overblown. So I think that's, if you want to look at the deeper questions of physics, if you're the frontier stuff, then you have to become more skeptical and look beyond just the headlines and the claims, and look beyond that, like what's being covered up. So I think there's a lot more to it. I mean, I have some ideas on what might be a better explanation than the Higgs, but I'm going to keep that to myself for the time being. but I think it's what we have for right now. And
quantum physics, as I understand it, says that that potentiality is how things work. That it's when you observe that it becomes a particle or a wave, and before that, it exists in potential different states. Is that accurate?
Sort of. I guess we have different ways of thinking about it, different people. I mean, mainstream quantum physics would say that there are these various possible states the particle can be in, and when you make an observation, then you kind of collapse it into one of those states, whichever one you happen to see it in. And the other ones kind of go away at that point. That's the conventional quantum view. Of course, that begs the question, what is an observation?
And what's a state? I mean, because state implies different dimensions.
Well, quantum physics kind of grew out of atomic physics, grew out of trying to understand particles back in the 1900s, what an atom is, and you have the electrons around the nucleus of the atom, and they have different states. There's some states that are kind of stable, and then it shifts between those states in a kind of a jumpy way to jump from one to the other, and so that was kind of their original quantum picture. And that picture itself was kind of a fudge, because when a particle is in a state, it's not radiating. It's not giving off any light or any energy. Okay, but their theory of electromagnetism that they had would tell them that that particle should be radiating, because you have an electron going around the nucleus in a circle very fast. It should be radiating light like crazy. And so the atoms all should collapse into little nubs. The electrons should collapse because they lost all their energy. So they had to answer that question. So they kind of answered it with a fudge. They said, okay, the stable states are the quantum states, and those are the ones where it does not radiate. And it has to do with the way the waves going around the path have to be an integer number of waves. If it does that, then it doesn't radiate. But it was not a very satisfactory way of answering the question. So it kind of told you, even at that early stage, there's probably something more going on here that they aren't dealing with. I'm getting off the topic a little bit. What was your question?
My question is, if things exist in potential, it implies there's different states, and I think that implies to me different dimensions, which is very interesting.
It does, yeah. What I have been doing in my own work, I've kind of come at similar from a similar point of view, a similar direction, um, because I also tend to suspect that when we say there's a particle sitting still, there's a lot more going on. Okay, and it does interact with the energy of the vacuum, the 0 point energy, and it is wiggling around, and there are little orbits, little motions, and we're not really counting them in our conventional physics. We kind of lump it and say, okay, well, it has a spin, and the spin kind of gives you a gross description of the fact it's going on in a circle, but it doesn't tell you much more than that. If there is more than that happening, then that would lead to something like my model that I proposed in my first book, the synchronized universe, because if particles go around in little circles, and based upon our theory of how electromagnetism works, they could radiate, but they would radiate in a very sharp direction, a very narrow direction, because they're moving so fast. They're going almost at the speed of light. The electrons are almost at the speed of light in these little circles. So when it radiates, it's like a little narrow beam, like a pencil beam of radiation, which then could affect some other electron far away. So it wouldn't affect all of the electrons, just only one other one. So if you take that idea, then you realize, okay, then in that picture, the electron could interact every so often with another electron very far away if the two motions happen to be synchronized. So they're looking at each other at that moment. Okay? Then they would feel a force from each other. They would say, oh, you're real, I'm real. And then the rest of the time, they wouldn't have any interactions. Okay? So if we have a whole system of particles like that, and they're all moving together in a synchronized way, they would keep interacting with each other in that way. And that would become your real universe. That's all you really are aware of. There could be other systems of particles that are moving in a different way. They're interacting with other particles, but you wouldn't see those. They're out of phase with your emotion. So you can have parallel universes overlapping, but they're just off by a certain phase or a certain frequency. So that was kind of what I was led to in the first book, and it explains a lot of paranormal phenomena. It explains how people can put their hands through walls and things like that. A lot of things get explained from that picture. So,
Well, could you make that specific? So psi phenomena can be explained by the fact that there's different states or different dimensions, or how would you say it that's accurate?
what it leads to is the idea that there are parallel dimensions, there are parallel realities, if you want to call them, that are separated by frequencies and phases, which means that you could shift from one to another if you knew how to change your frequency or change your phase. It means that what we call quantum noise is probably the interaction of other systems that are out of phase with our system, kind of bumping into our particles in a random way and making it look random. But most of the things in quantum physics involve cyclic constant frequencies. So I think it gives you a different way of coming at explaining quantum physics. That's what I think. And I need to work out a full mathematics, and I have not done that. So I've got a lot of pictures and hand waving and parts of it that I've done, but I haven't really done a full mathematical model of it.
People who do astral travel like Robert Monroe or have near-death experiences like Eben Alexander, they
Right.
go to those states and come back, alternate states.
Exactly. That's right. Exactly.
So they're a different frequency or a different vibrational
Right.
field.
Exactly. So you, by shifting your consciousness, you can. The consciousness really probably involves changing our frequency and phase, so we can hook into some other parallel system.
And you know the Monroe Institute uses diurnal
Hemisync.
hemisphere to
Hemi-
get people to astral travel. So that implies that people can be taught how to astral travel.
Right. Right. Exactly.
Have you done it?
I have to some extent. I'm not very good at it. My left brain gets in the way. I've been to Monroe Institute a couple times.
Uh,
I just retired from being on the board of Monroe Institute, in fact. Um, and I've been out of body a little bit, a couple times. Actually, the best out of body experience I ever had was probably doing remote viewing. I took remote viewing courses at Farsight in Atlanta, and oftentimes in those you also end up out of body because you're focusing on a target that may be elsewhere. Can you excuse me for 1 second? I've got to take a bathroom break. Is that okay?
Me too.
Okay, well, good. I'll meet you back here.